Hey, welcome back to another Just 5 Mins. Got an experimental special episode this time around, and yes, it does feel like I've cheated a little bit. I'll be honest, but I have done some research about this. But I've used AI to actually generate Ms. AI and Mr. AI to explain all things LLMs, vectors, search, and quantization, and it was really just an experiment to see how well this will actually sort of work. And I think obviously there's going to be a situation where, yeah, everything is just AI generated and nobody cares anymore. But in this case, I have to say, I got the I've been doing the research on how vectors work, search, and quantization in LLMs, and I'll let the kindly AIs to explain what I'm talking about. But the idea is, I put together, I edited the all the text that I've been researching for the last few weeks. But yeah, the audio production is AI. But anyway, the interesting thing, I listened back to it, and it is quite engaging, probably more so than my voice. So there you go. Maybe I'm out of a job. But anyway, take a listen if you want to understand how vectors work. What are vectors anyway? What the heck? It is actually quite good because it does explain them in very simple ways. But how do LLMs work with these things called vectors, and how does it search? And what the heck is this quantization that they talk about? So ultimately, a little giveaway is quantization is having these large language models, not the huge language models. I have to be very careful there. But it allows those certain LLMs to basically run on much smaller devices like your laptop or even a phone and things like that. Anyway, hope you enjoy. Let me know in the comments if you find it interesting and engaging or not. It's a little bit of an experiment, but I'm going to leave it there and introduce the AI presenters.
Welcome to the deep dive. Today, we're really getting into the weeds with AI, specifically large language models. You know, those tools so many of us use daily. We're going to try and unpack how they actually understand us, how they generate those, well, surprisingly good responses sometimes, and even how they manage to shrink down to run on, say, your phone. It's pretty fascinating stuff when you look under the hood. So, our focus today is on two key things. First, vectors, how LLMs use these, well, mathematical things to represent and find information. And second, something called quantization, which is a really clever way they make these huge models work in the real world on actual devices. We've been digging into some great material, especially one piece called LLMs, Vector Search and Quantization Explained, really helped clarify things.
Yeah, it's a good one. And our goal here today really is to give you those aha moments, to connect the dots, between how these AIs work technically and what that actually means for you, how you use them, maybe even how you think about them. Because understanding the how behind the magic, it's not just interesting, it shows these aren't just black boxes. They're built on, well, some pretty sophisticated logic.
Okay, let's dive in then. So you type a question into an AI, or you talk to it. How does it even start to figure out what you mean? It's not just keywords, right? It's got to be deeper than that.
It is. It really starts with these vectors you mentioned. Basically, everything the LLM works with, a word, a sentence, whatever gets turned into numbers, a list of numbers. That's the vector. We often call this an embedding. And the amazing part is these numbers, these vectors, capture meaning, semantics. So concepts or words with similar meanings, their vectors end up being numerically closer together in this huge multidimensional space.
Multidimensional space.
Okay. Yeah. Hard to visualize, but think of it like a map. So the classic example, dog and puppy. Their vectors would be really close on this map.
Because they mean similar things.
Exactly.
Yeah.
But dog and, say, car, much further apart.
Makes sense.
And this closeness, this proximity, that's how the model kind of implicitly gets relationships. What's really key here is that the LLM isn't like a database. It doesn't have a list of facts stored explicitly. Instead, all that training it does, that adjusts billions of parameters. And those parameters encode all these patterns, these relationships, this map of meaning.
Okay, so it's not looking up dog in a dictionary file. It's navigating this map you're talking about. So how does it find the right spot on the map or the right patterns, to answer my question? If it's not a database search, how does that work? That sounds really complex.
It is complex, but there's a logic to it. This is where nearest neighbor algorithms come in. It's kind of the search part. So first step, your input, your question. It gets turned into its own vector using the same system.
Okay, so my question becomes a point on the map too.
Precisely. Now, step 2. The model needs to find other points, other vectors on the map that are similar to your question's vector. For this, it uses math, often something called cosine similarity.
Cosine similarity.
Think of it like angles. If two vectors are pointing in very similar directions on the map, the angle between them is small. That means they're similar in meaning.
Got it. So it's looking for vectors pointing the same way as mine.
Pretty much, yeah. Which leads to step 3, the nearest neighbor search. The model finds the vectors that are closest, the nearest neighbors to your input vector. These represent the most relevant patterns or concepts it knows. Now, searching through billions of points is slow, right?
Yeah, sounds impossible.
So it uses optimized algorithms, things like KD trees or ball trees. Think of them like super efficient indexing systems for this high-dimensional space. And for the really huge models, they often use approximate nearest neighbor search, ANN. Yeah, it's much faster, more scalable. It finds points that are very likely the closest, maybe not always the absolute mathematically perfect closest, but close enough and way faster.
Okay, a slight trade-off for speed.
Exactly. And then the final step, step 4. Based on these neighbors, these relevant patterns it found, it doesn't just pull out a pre-written answer, it generates a response. It predicts the most likely next word or token, then the next and the next, building the answer dynamically based on everything it's learned and the context it just retrieved.
Wow. Okay, so connecting this back, it's really not like searching Google. Google finds existing pages. It creates the answer.
That's the fundamental difference.
Yeah.
It's dynamic generation based on learned patterns, not retrieval of stored data entries.
So what does that mean for, for us using it? It means the AI isn't just repeating things. It's actually trying to understand the nuance, the context of what you ask.
Right, and then it crafts something new, something specific to your query, more like a conversation.
Which is why it can do things like summarize or translate concepts, not just words. It gets the meaning.
That's a big deal. It really is. It changes how we interact with information fundamentally.
Okay, but you mentioned billions of parameters. These models sound huge. And powerful, yes, but huge. That seems like a problem. How do you get something that massive to run on, well, my phone or some other small device? You can't fit a supercomputer in your pocket.
No, not yet anyway. And you've hit the nail on the head. That size is a major challenge for deployment.
So how do they solve it?
This is where the second piece comes in, this technique called quantization.
Quantization.
It's a really clever engineering solution. Basically, quantization is about reducing the precision of the numbers inside the model, those weights, the parameters we talked about, and the activations, the signals flowing through. It makes their numerical representation simpler.
Simpler how?
Well, models are usually trained using high-precision numbers, typically 32-bit floating point numbers. They can represent a huge range of values very accurately. Quantization reduces that. It maps those high-precision numbers down to lower precision ones, like 16-bit floats or even 8-bit integers.
Integers, like whole numbers.
Yeah, exactly. Think of it like, imagine you have a million shades of paint. That's your 32-bit float. Super precise. Quantization is like saying, okay, we're only going to use 256 standard colors.
Okay.
So any of your original million shades, you just pick the closest one from the standard 256. You'd lose a tiny bit of nuance, maybe.
But you're dealing with way fewer options.
Exactly. It makes the representation much simpler, smaller to store, and faster to compute.
So does this happen after the AI is trained? Or like during the training?
Right.
When do you simplify the numbers?
Good question. It can happen at different times, and that affects things. There are two main ways. One is post-training quantization. You take a fully trained, high-precision model.
The one with a million paint shades.
Right. And then you convert its weights to the lower precision format, the 256 shades. Sometimes you use a small bit of data to kind of recalibrate it, adjust things slightly to minimize any accuracy loss from the conversion. It's usually simpler to do.
Okay. And the other way?
The other way is quantization-aware training. Here, you actually incorporate the lower precision, the constraints of quantization, during the training process itself.
So it learns with the simplified numbers from the start.
Exactly. The model learns to work within those constraints, to adapt its parameters, knowing they'll eventually be represented with lower precision. This often gives better results, less accuracy drop, because the model is kind of optimized for being quantized right from the get-go.
That makes sense. So this whole quantization thing, it sounds like a game changer for actually using AI everywhere. What are the big wins you see from it?
Oh, the gains are huge. First, model size. It drastically reduces the memory footprint. The model takes up way less space. Crucial for phones, small devices.
Okay, smaller files.
Second, speed. Inference speed, how fast the model responds, gets a major boost. Calculations with integers are just way faster for processors than complex floating point math.
Faster answers. Nice.
And third, energy efficiency. Lower computational needs mean less power consumption. Think battery life on your phone or wearables.
Right, less battery drain. Okay, those are big advantages.
Absolutely. It's why quantization is so widely used for AI on mobile apps, edge devices, IoT things. Anywhere resources are tight.
But what about that paint analogy? Losing the shades, does it hurt the accuracy? Is there a trade-off?
There can be a trade-off, yes.
Yeah.
Reducing precision can lead to a small drop in accuracy. But, and this is key, when quantization is done well, especially quantization-aware training, that accuracy loss is often tiny, like really negligible for most applications.
So usually worth it?
For a vast majority of real-world uses, absolutely. The gains in size, speed, and efficiency far outweigh a tiny potential dip in raw accuracy. Now, if you're doing, say, super-sensitive scientific calculations where every decimal point matters, maybe you stick with full precision.
Sure.
But for most things you and I interact with, quantization is what makes it practical. It's really about democratizing this powerful tech.
So the next time my phone suggests the next word I'm typing, or an AI filter works instantly on a photo, there's likely some clever quantization going on behind the scenes, making that big AI model run right there in my hand.
Very likely, yes. It's that intricate engineering, these clever tricks like quantization, that bridge the gap between massive research models and useful, everyday AI features.
Wow. Okay, so today we've really peeled back some layers. We looked at how LLMs represent, meaning using vectors, these points in a conceptual space, and how they search that space using nearest neighbors to understand us and generate responses dynamically.
Yeah, moving beyond just simple data lookup to actual generation.
And then how quantization tackles the huge size problem, making these powerful models small and efficient enough for our phones and gadgets.
Ensuring the technology isn't just powerful in a lab, but practical and accessible out in the world. It's really a combination of conceptual breakthroughs and clever engineering.
Yeah, understanding these bits really gives you a new perspective, doesn't it? You see, it's not just magic. There's this elegant logic underneath it all, constantly being refined, too.
Definitely. Which kind of leads to a final thought, maybe for you listening. As AI keeps getting more efficient, running better on smaller devices, thanks to things like quantization, what happens next? What new kinds of maybe personalized AI applications or interactions do you think we'll start seeing? Where might this pop up in your daily life in ways we haven't even thought of yet, now that it can live right there on your device?